Happy Halloween, everyone. Welcome to today's webinar titled Metrics and Statistics Don't Have to Be Scary. I'm Matt Banna from KaiNexus, and I'll be your host for this webinar House of Horrors today. I think I make a pretty good Captain KaiNex America. I don't know what's going on with Mark Swedish Chef exactly. Is that what you were?
Yeah, it was a costume I rented. Happy Halloween, everybody, and Matt. Yeah, I don't know what's going on with the nose. That wasn't real. That wasn't quite right. But I almost forgot. I do have a costume on today, and I think it's relevant to our topic of what's sometimes called control charts. Can you see me?
Well, what are you exactly?
I'm a out of control chart.
I see that now with the shirt and your hair's on fire and everything's going. I get it.
Control charts. Anyway, we'll get into that. Sometimes called process behavior charts. We're going to try to have some fun here today. So thanks for coming along on the ride.
Anyways, here are the hellish logistics for today's webinar. Now, the presentation will be about 45 minutes or until the time runs out. We have 10 minutes for a Q&A session, and then you can use the GoToWebinar meeting panel to submit a question at any time if you dare. Agul will deliver recording links and slides via email, so you can check your spooky spam folder if you do not see that come through, and also see the handouts feature for our slides today and the chat box as well. Mark?
I'm sorry, those are not in the handouts box, but we will send the slides to everyone after the fact.
Perfect, thanks for the correction there. So here at KaiNexus, we've enjoyed Mark's latest book, Measures of Success, React Less, Lead Better, Improve More, and it's taught us a lot about understanding variation, managing metrics, and leading improvement. Me personally, I'm currently in the middle of it. It's a great read and it's super easy to understand. Highly recommend it for all of you. It's currently available as an ebook, and a paperback version will be available soon. Now, Mark is a senior advisor to KaiNexus, and he's been with the company in various capacities since 2011. He has a Bachelor of Science in Industrial Engineering from Northwestern and a Master's in Mechanical Engineering and an MBA from MIT. I'm sure both schools are very proud of you and your costume, Mark. I'll hand it over to you.
Yeah, I hope none of them take away my degrees for trying to have a little fun as we learn something today. As Matt mentioned, my most recent book, here's maybe a little bit more Halloweenish version of that cover. We're trying to help get people off the roller coaster of metrics, if you will, where there's just a lot of reaction back and forth. People post numbers, they post charts. We might see some red and green color coding, and hopefully we don't feel like this guy who's just going down and crashing on the roller coaster. Even when there's ups and downs, that can be a bit spooky or a bit scary. I've worked in organizations, and maybe you feel the same way, where we see kind of zombie-like managers or executives just kind of slow roaming the hall, and they're looking for metrics boards, and you hear them in the distance, reds. They're looking for red metrics. So then these executives might say, you must root cause your reds. And this is pretty frightening. I think this is scary to me, this idea of zombified managers roaming the halls. Why is this scary? Well, not every red is worth reacting to in that way of looking for a root cause. And with some of the methods I'm going to share today, we can start distinguishing between meaningful changes in a metric and what you might call noise. And we can learn to look at our metrics in a way that's not just this breakdown of red or green. Because when we react or overreact to every red, or we overreact to every worse than average data point, or we make people look for a root cause for every small change in a metric, instead of a time suck, we might think of that as being like a vampire who says, I want to suck your time. And keeping with the Halloween ghoulish theme, I think the only ones who don't care about time are, well,
Mark, I mean, I know it's Halloween, but that got a little dark there.
Yeah, you're right. Sorry about that. We'll lighten things up the rest of the way here. Thanks for pulling the andon cord on that banana. Sorry for the grave tone. Well, one of the, I think, facts of life is every metric has variation, even if that's sort of frightful to think about. I think a lot of managers, a lot of leaders, process improvement people perhaps are of the mindset that a consistent process should deliver consistent results. Well, and if we play the red bead game from Dr. Deming, that's something I use in my workshops. You can go Google that, or look for something on YouTube about the red bead game. That game illustrates in a fun way the idea that a consistent process will always generate results with some level of variation. So the question is, well, how much variation? So within KaiNexus, we kind of practice what we preach. The KaiNexus team has learned from me about what you can call control charts or process behavior charts. Within our KaiNexus software, we track key metrics. And one of the metrics I track that you see here is the number of people who register for each of our presentation style webinars. And I'll explain later some of the detail of this control chart, but you can see the black line is the number of registrations. And we can see there is variation. There are many, many causes of this variation. We can't always put a finger on it, especially when the metric is just fluctuating within that range that's below what we call the upper control limit or the upper natural process limit. On this chart, the dashed line at about 260 represents the average number of registrations. And as we see the number of registrations fluctuating over time, guess what? About half the time we're above average and half the time we're below average. That maybe shouldn't be too unexpected. Now, the second dashed line is what we call, again, that upper natural process limit. We had one webinar in 2017 where you can see there was a big spike in registrations. And this is actually a webinar by Jess Orr talking about applying A3 problem solving to everyday life. We think, we had a huge spike because of really good LinkedIn promotion by Jess and maybe by me. But then again, we tried to repeat a lot of that same playbook with a follow-up presentation by Jess, and we didn't get anywhere near the 730 registrations we had that day. So when a chart like this shows us the difference between signal and noise, that signal is worth reacting to, and we might not always find the answer to the question of why we had a point that's out of control, and that's what we see here on my t-shirt, an out of control data point, or we could call that a signal. But then we went back to sort of fluctuating around the average. So we can try to figure out how to improve the overall system that might lead to higher registration numbers, but we might not find the answer to that necessarily in analyzing any of these other data points. Our best bet might have been trying to analyze the signal from Jess's webinar, and we still haven't cracked the code on that. For today's webinar, the last I checked about 20 minutes ago, we had 330 registrations, which you can see there. Well, that's higher than last time. It's not as many registrations as Jess's first webinar, but I think we wouldn't get too excited about this single data point. It's part of the routine variation in this metric in our webinar process, just as I've learned not to get too upset about that previous data point. Our previous webinar, which was an excellent webinar, and it's in our webinar library like all the rest, but that 200 registrations is not anything to freak out about. So in the use of control charts or process behavior charts, we learn, hopefully, not to get too excited, not to get too upset, not to freak out about noise in our metric. And I'll talk about that more later on. There's a question we might face tonight if we're running out at the last minute. How many trick-or-treaters should I plan for? How many are going to come to your house? You might gauge that based off of last year's number, if you remember or keep track or at least vaguely know how many treats you gave away. But that number of trick-or-treaters, I would almost guarantee, is going to fluctuate every year, especially if you live in an area with a stable population, stable in number of kids, or if that number is increasing, we can use control charts or process behavior charts to help us understand if we're seeing fluctuation or a meaningful shift in the number of trick-or-treaters. So I don't have the data, but one thing I remember as a kid, and my parents, I lived in the same house with them from first grade through high school. My parents are still there. They've been there for more than 40 years. If they're watching the webinar, I hope they're not the wig in my performance today, in my costume. But they tracked the number of trick-or-treaters. They would write it down on a piece of paper, and I don't think they kept that data. But I'm going to build a scenario here, assuming that they might have, and what we might have learned from the number of trick-or-treaters over time, or at least the count of those trick-or-treaters. And we're being interrupted by, I said we're going to keep it light. Did you say count? Yes, we counted the number of trick-or-treaters. Thank you, Count Von Count. So that number, those numbers might have looked like this. So if we look at a list of numbers, a table of numbers, sometimes in the workplace, a table of numbers gets posted and it's called a dashboard. It might look something like this. We might have red or green. And again, our zombie managers, I hope I haven't offended anybody, our zombie managers are roaming and looking for reds to react to. It's really hard for people to detect trends, meaningful trends, from a list of numbers. We can't distinguish between signal and noise. And we look here and we see, well, gosh, we've got about half red, half green. Are the reds really worth reacting to? Do we have routine variation and nothing but noise, or do we have meaningful signals that are really worth paying attention to? So we might ask, do we have a crystal ball? Can we predict the number of trick-or-treaters we'll have in the future? Can we predict what the performance of a future metric is going to be? And this crystal ball clip art here, and that sort of triggers me a little bit. I'm like, no, I'm upset. It's not a column chart. Column charts, and this is a different discussion for a different day. I don't think, and there are people who've done more research in the visual display of data, that column charts are a bit misleading visually, because our eyes, there's a real detail point here, but our eyes get drawn to the middle of the column when really the business end of the column, the data point, is at the top. So that's why run charts, where we actually see the dot or just where the line is going, visually does less to kind of fool our brains about what's happening with the data. And I'll be careful saying brains, because maybe those zombie managers are also looking for brains instead of red data points. But we can ask, do we have a crystal ball? And as we look at our metrics, do we have methods that help us answer a couple of key questions? I mean, the reality in organizations is we're going to be asked, are we achieving our target or our goal? Are we doing so sometimes, never, consistently? I think the reality is that this matters in organizations we work in. So that's the red and green. But we also need to answer the question of, are we improving? What is the trend? Is there a signal of a statistically significant shift, a meaningful shift in our metric? And then there's also key questions about, how do we improve? We can't just always do that reactive, explain, root cause analysis response to noise in the system. That ends up being a time suck. It ends up being a waste of time. But when we have a stable, predictable system that's not consistently achieving our goal, we can ask questions about, how do we improve the system? And we'll share examples of that here in a bit. So I think, compared to a list of numbers, a run chart can really help quite a bit. So here's a run chart from that, again, admittedly made up data of the number of trick-or-treaters coming to my parents' house in Livonia, Michigan in the 1980s.
Hey, you have a pretty serious dip there, Mark. You have a couple dips. You give out vegetables or almond joys some of those years to get that dip?
I don't know if there's a root cause worth looking for, Matt. That's there may or may not be, right? So we've got our 3 key questions. Are we achieving our target or goal? Well, I don't think we didn't really have a goal. So we didn't have red or green, but we can ask, are we improving? Is the number of trick-or-treaters changing significantly? And then in a workplace, we might ask, how can we improve? So I think that the key question for the trick-or-treaters is the number consistent? How would we plan the amount of candy or vegetables? Maybe we got a bad reputation the year. I should have plotted the number of tricks. I don't know if we have data on that. This question of, can we predict future performance? So to do that, we need to first filter out the noise so we can look and see if we have any signals in the metric. If we don't have any signals, we can conclude that it's a predictable metric, and I'll show you in a minute how I could predict the range. I can't predict the number of trick-or-treaters that would have come in 1991, but I could predict the range, which might be helpful enough for planning purposes. So I've learned a lot of this methodology from Don Wheeler and his outstanding book, Understanding Variation, the Key to Managing Chaos. And Dr. Wheeler was kind enough to write the foreword for my book. What's done is done, so I'm going to give him a Halloween mask, and hopefully he won't take away the foreword from the book. But Dr. Wheeler says, while every data set contains noise, again, remember, every metric will have some variation, even if it's minuscule. Some data sets may contain signals. Therefore, before we can detect a signal within any given data set, we must first filter out the noise. And that's what we use process behavior charts for. So if run charts are helpful, process behavior charts help even more. So ignoring the math for a minute, this is what a process behavior chart would look like. We saw an example earlier where we plot the number of trick-or-treaters, we calculate an average for that baseline time frame, and I kind of arbitrarily chose 10 years as a baseline. That's okay from a statistical standpoint. With workplace metrics, it's better to have 15 to 20 data points as a baseline. I mean, you can do it with as few as 6 or even 4 if that's all the data you have. But realizing that the calculated limits are not going to be really as reliable as they would be with better baseline data. And so I'll talk about the calculations in a minute, but we calculate the average and we see, well, some years are above average, some years are below average. We might be tempted, and this is scary for different reasons, we might be tempted to draw a linear trend line. I'll show an example later, and linear trend lines might end up being misleading, unfortunately. But here we calculate, and they're symmetrical around the average, a lower natural process limit and an upper natural process limit. Now, I'll show you some examples in a minute, the rules we would use to determine if there's a signal. But for now, it's just, if you'll trust me, there are no signals in this data. The baseline data suggests very strongly that it's just fluctuating around an average of about 41 trick-or-treaters. Now, if I were going to buy candy in 1991, and if I wanted to make sure I don't want to run out of candy because I might get my house egged, and I don't want to buy too much candy because, well, I shouldn't have a lot of extra candy around the house to be eating leftovers. So the upper natural process limit tells me that based on previous variation, I think the number was about 52. We really wouldn't expect to have more than 52 trick-or-treaters unless something changed in the system. We might know, let's say maybe a new subdivision was built a couple of streets over, and there's more houses and there's likely to be more kids in the neighborhood. We might anticipate that we think the system is shifted, but without knowledge of something that might describe a signal, our best prediction might be to assume that future years are going to be like the past. So it's not a perfect crystal ball, but the process behavior chart methodology actually does allow us, with different business metrics, to predict within this range of what our future performance is going to be. Again, unless the system changes. So there are some rules and signals that we can use to tell us if there's likely a signal or of a system change. Or if we've intentionally made a change to the system, we can use process behavior charts to help prove some of the cause and effect analysis. So we're going to enter now. This might be a little bit scary. We're going to enter the math zone. Enter if you dare. Are you willing to come with us, Matt?
I am.
Is the math scary? Well, it's not scary, but you have to dare to dive in. And at the end of the webinar, we'll give some other resources. I explained this in my book, Measures of Success. We've got previous webinars that were not full of Halloween fun that explain how all this works as well. But a couple of key points and steps in the process here. We plot our data. We calculate the mean or the average of our baseline points. And then the next column in the spreadsheet or whatever software you're using might include, should include the moving range, which is basically just the absolute value of the difference between every two data points. So this gives us a way of estimating the level of routine variation. The technical term, I think, would be to talk about the dispersion of the data. And a key thing with this process behavior chart methodology, which is sometimes called the XMR charts, is that we don't use a calculated standard deviation. We use the average of these moving ranges, and there's a number of really kind of wonky technical reasons. If anyone wants to email me afterwards, I can send you some references to some Don Wheeler articles about why we use the moving ranges. In a nutshell, this is much more robust for real-world settings and real-world data. So to calculate our natural process limits, we calculate the MR bar, which we might, that's the average of the baseline. MR bar is, I guess, wonky math talk for saying the average of the moving ranges. But then we calculate the lower and upper limits by taking the average or the mean, same thing really, plus minus 3 times the MR bar divided by 1.128. I think out of scope for today's discussion, the 1.128 is a statistical factor that allows us in this methodology to basically estimate the plus or minus. You could think of them as 3 standard deviation limits above and below the average. It's an estimate of the standard deviation instead of using the calculated standard deviation. And again, you'll just, for now, maybe just trust me on that. There are deeper dives in Don Wheeler's books and articles that will help explain that more. So again, we've got the X chart. We have the data, we have the calculated mean or average, and we have the calculated, again, just to emphasize this point, the calculated upper and lower natural process limits. This is the voice of the process, whether we find it scary or not. But I mentioned a minute ago the XMR chart. So we have the X chart. The X chart often has a buddy. We call it the MR chart. So we plot those calculated moving ranges for each of those data points. And then we calculate an upper limit. We can call it the upper range limit for this chart, which comes in at about 15. So when we talk about finding signals, and when I show you that in a minute, we're looking at the X chart, looking to see if there are signals that tell us something has likely changed significantly in our process or our system. And then we also want to look for signals in the MR chart. If we have a huge jump from point to point, then that's another indication of something changing in our systems. So we've gotten into a little bit of math. Let's see if we can have some fun here in a second. So we are going to invite to the party those of you who might not know the Saturday Night Live sketch. David Pumpkins is a Tom Hanks character from SNL last year. If you haven't seen this, just go to YouTube after the webinar. But David Pumpkins would introduce himself as, "I'm David Pumpkins, and my charts are going to scare the hell out of you.
I mean, I'm just trying to wrap my head around process behavior charts.
Well, I'm David X Chart Pumpkins, man.
And the other chart is
part of it. All right, that's enough of my poorly thought out David S Pumpkins, David X Chart Pumpkins dance from the video.
I appreciated it.
I've probably just embarrassed myself, but the MR chart really should be part of it. So if we look at the complete pairing of charts and what we would call a process behavior chart, these charts are typically shown above each other. They have the same time scale. We have the data in the X chart, and we have the MR chart below. Now, there are times and there are arguments for, maybe in the real world, this is a bit much for people to handle. So there are times we might just show the X chart, but I think it's important to understand when we might see a signal in the MR chart so that we can maybe intuitively look for that in the X chart. So let me explain and show these rules for finding a signal when we look at these charts. We don't just guess. This is based on math. So there are 3 rules for detecting a signal in the X chart. Rule 1 is looking for any data point that is above or below the calculated limit. So this is a strong signal that something has changed in the system. This is unlikely to have happened by chance. Rule 2 is looking for 8 or more consecutive data points that are above or below the average. This is also statistically unlikely to randomly happen. It's a signal that we've had a shift in our process. And then rule 3 looks for a clustering of 3 consecutive or 3 out of 4 points that are closer to the limit than they are to the average. Now, rule 1 also applies to the MR chart. Now, if I were showing the MR chart for this data, look at the big jump between this data point and this data point, the big jump between this one and this one. The MR chart is going to show those jumps. Now here we've seen, okay, there's a signal that something changed, here's a signal that something changed. The MR chart would likewise show signals. But there are some special cases, maybe some rare cases, where this April 14th data point was just above the lower limit, and then we jumped up to here. The X chart wouldn't necessarily show a signal, the MR chart would. So if we don't let the MR chart be part of it, we do run the risk of occasionally missing a signal, which means missing a signal, missing an opportunity to better understand our process in a way that can better drive improvement. So applying this to the trick-or-treat situation, let's say in 1991, we actually had, let's say, 60 trick-or-treaters come to the house. The chart tells us something has changed. Whether it's with trick-or-treaters or any workplace process, it doesn't tell us what changed. We need to understand our system. We maybe need to go to the Gemba. We need to go talk to people and figure out what the cause was. Did a bunch of high schoolers suddenly decide it was cool to start trick-or-treating? We might not know the answer, but now I would say going forward, the system is no longer predictable. We don't know yet if 1991 was a one-time spike and we're now going to be fluctuating around a higher average, or if it was just a rare one-off occurrence. So we might see over time what you might call a sad decline in treats, where now that number goes back down and we have 8 consecutive data points below the average number of trick-or-treaters. This would be a signal to me that something has changed. Maybe a bunch of neighborhood kids have graduated and there aren't as many young kids in the neighborhood anymore. That's maybe a realistic explanation. But again, the process behavior chart filters out noise so we can identify signals. Everything from 1980 to 1990, that was all noise. And then we start seeing some signals. That's worth reacting to. Each of those ups and downs within the realm of noise or routine variation, not worth responding to. So we've got a KaiNexus story we want to tell real quick. Our CEO and co-founder, Dr. Greg Jacobson, He's a really good leader. He's a reasonable guy. He doesn't get upset about stuff. He is systems focused. He's a good lean thinker. But a lot of leaders sometimes tend to, maybe if you will, howl at the moon, even though Greg wasn't howling. He would ask Maggie Millard, our marketing director, why were the number of leads down last month? Again, not angry, not upset, but just asking a question. You might ask, well, leading by asking questions is good, right? He's just being inquisitive, right? So it's not the worst leadership behavior by any means. But Maggie would respond and say, I don't know, let me look into it. And Maggie was kind enough to share, this is from last year, couple's costume for Halloween. This is a different kind of geeky costume. Shoulder clips, and she pointed out Zach behind her as the sun has a corona around him, which I applaud. Good job, good job. So Maggie would go, and I'm going to embarrass Maggie by leaving her picture up on screen here. Maggie would go and dig through the data and try to come up with a reason why. Might not have been an explanation because we were looking at tables of numbers or just looking at two comparison points. So going back to the David Pumpkin sketch, the skeletons would ask, ready or not? Here we chart.
Mark, how much David X chart pumpkins is in this?
Look, it's in 37 out of 100 slides. They're not all going to be winners, okay? Oh, seriously, no.
You're out of control.
I'm out of control. The chart tells you so. It's not the red hair, it's the chart. Oh, I just realized. You might have thought, boy, not as much thought went into the costume as you might have thought. But here was our run chart. When we charted what are called the tier 1 leads, it says weekly, it was actually a monthly chart. The number's up, the number's down. It's higher and it's lower. And so if Maggie were to go and look for an explanation of that data point, why was the number lower than the month before? She might have ended up doing what Don Wheeler calls writing fiction. And unless we are Edgar Allan Poe or Stephen King, we don't want to waste people's time writing fiction. And I'm facing the horrors of PowerPoint, and there we go, having a delay. Updates to the Mac OS and PowerPoint have been scaring me recently, so I'm glad we're still up and running, right, Matt?
Yes.
Don't waste people's time writing fiction. We didn't want to waste Maggie's time. If she spent an hour digging through the data, that's an hour spent not improving the system in ways that would have boosted the average number of leads. So let's look at a chart and see what we would have learned from that. So if we drew a run chart, it might be tempting. You see the purple dashed line, that is a linear trend line. It's really easy to add that in Excel with 2 clicks. But the linear trend line is misleading in a lot of ways that I won't get into today. If you're curious about this, I can point you to some references, and I cover this in the book. And linear trend lines are really sensitive to, we happen to have a really low data point at the beginning. We've got kind of a high data point at the end. It's really easy to come up with situations that are the Schrodinger's cat of charts, in that it could be both increasing and decreasing, which is maybe scary in some sort of weird hall of mirrors sense of, we don't know what we're looking at. It's really sensitive to the range of data points we use. It's really overly sensitive in a way that a control chart or a process behavior chart would not be. So I think this is why one reason why process behavior charts are more helpful, and why I've tried to coach the KaiNexus team on this. So this is a process behavior chart for the leads. And because the calculated lower limit would have been negative, we don't really put that on the chart. This is the count of the number of leads. Hopefully Sesame Street count stays away. I think he's flying away like one of these bats here. Here's the average. And then we calculate an upper natural process limit of about 20. And the lesson we learn is that all of these data points are, again, noise. There are no signals that the system that generates tier 1 leads does anything but fluctuate around an average. So if we ask, why was this number high? That's just as unlikely to come up with a root cause as this number here that's low. The same system is generating a different number of leads in each time period, and that tends to happen. So instead of looking for a root cause here, we could try to improve the system. Maggie could spend that hour writing a clever blog post or coming up with other ways of letting people know about the company in a way that would increase traffic to our website and would increase the number of leads. So over time, as Maggie was making improvements to the system, we eventually see a signal in the chart. Now, again, you could draw a linear trend line here, but a linear trend line implies that the number is going to go up forever, which might not really be true. The statistical reasoning behind this does encourage us to look and see, well, we see 8 consecutive points above the average. Here we actually see a rule 3 signal of 3 consecutive data points closer to the limit than the average. So that's actually the signal we would have seen first. And then eventually we see this rule 1 signal, which is also the 8th data point in that grouping above the average. So these signals would give us confirmation that Maggie, the broader system, that something positive was happening here. We've made a change to the system. So then, before we saw the increase, though, one point I should have made previously was that we calculated that limit. We see that here the limit was at 20. And we'll come back to Maggie. We'll give her a fun scream mask here because she wasn't screaming, but her reaction was like, oh, but I don't like those limits. They're too wide. But, and this happens a lot. This is typical reaction, a common reaction, where people look and say, well, I don't like those limits. Well, those limits are calculated based on the inherent variation, the amount of routine variation in the system. So if we don't like the width of the limits, we could try to do things to reduce variation in our process, reduce variation in the output of our process. So we saw a signal that was finally up above those limits. And then we could look and ask, well, have we established a new average? Are we fluctuating around a new higher average? And we can look and say, well, we don't see any signals based on that, but we might have a system now that maybe in an acceptable way is less predictable than it was before. Eventually, we might have had another data point above the newly calculated limit. Maggie might not like how wide these limits are, but they are, again, the voice of the process. There's a different, slightly more complicated way of doing these charts that looks at, instead of a horizontal average, if we have a system that's increasing at a fairly consistent rate, we can actually draw, in this point now, we would call it a center line that's increasing at a rate of increase of the metric. And then our lower and upper limits then start increasing, again, in a symmetrical way around that center line. So over time, we could start looking for rules of a signal. I would look and see, well, this is now a predictable system, and instead of being predictable around a flat average, it's predictable around an increasing trend line. But linear trend lines sometimes fail us, and over time, we see the number of leads then starts to flatten out. And the process behavior chart tells us this because we now see 8 consecutive points below that center line. We see data points that are below the lower line there. So what we might have had happening was a flat period, a period of increase, and now we're probably fluctuating around a horizontal average. It would be impossible to get that type of insight from the data if we were just looking at a table of numbers, a quote unquote bowling chart as they're called sometimes, We wouldn't get that insight if we were just comparing each data point to the last, being happy when the number is higher and being sad when the number is low. So we need to use process behavior charts to help teach us when to react and when to step back and improve the system in a systematic way, maybe using A3s. So again, we may attract the zombie managers who are walking around looking for reds, and hopefully they're slow zombies and at least we can outrun them, but they may cause a bit of havoc in our process. So let me share a couple other examples before we wrap up here. I said earlier, not every red is worth reacting to in the same way. This is especially true if we have an X chart where the goal happens to be at or very close to the average. This is a predictable system that's fluctuating within the range of these lower and upper limits. It's fluctuating around an average, and guess what? We've got some data points that are better than average. Those are the greens. We'd say hooray. Then we have some that fluctuate into the red, where it's the zombie apocalypse. So the lesson from this is stop overreacting, or don't overreact. Don't get too excited about this data point and assume it's going to continue trending upward. And don't freak out about these points that are below average. So instead of asking for a root cause for that data point, we need to figure out how to improve the system. So in some scenarios, not all reds are a signal that something has changed or that it's worth reacting to. So we might improve our process in a way that ends up looking like this. We have a predictable system where we see the average is well above the goal. The variation is relatively low, so our lower natural process limit is higher than the goal. So unless something changed, we could probably feel pretty confident that this metric is going to continually, consistently provide the results that we're being asked to provide. But what happened here? We had a point above the upper limit. And if we view all greens as equally good, we would have missed that signal and that opportunity to understand what changed in our system. Likewise, there's this data point below the lower limit that is also a signal that something has changed in the system. But if all we're doing is reacting to the reds, this would be a missed signal. It would be a missed opportunity to understand more about our system. It might be a missed opportunity to intervene before, let's say, things drop down into the red. This is the type of time when it's really helpful to ask what changed, what happened, look for a root cause or what's called a special cause. We could go and investigate, when that would probably be just a waste of time trying to explain that data point that's down within the range of routine variation. So I think, all right, what are the things, these aren't things that keep me up at night, but I think, all right, the horror of the mistakes we can make. The first two mistakes are kind of related. Don Wheeler writes about them in the foreword to my book. When we overreact to noise, or when we miss signals. We, in the first case, waste a lot of time when we overreact to noise, and when we miss signals, we miss opportunities to improve the performance of our system. A couple detailed mistakes that people sometimes make is confusing the natural process limits with a goal or a target. They confuse the idea of looking for a signal, or what we might call an out of control data point. This is handy to have this on a shirt. We can point to the out of control data point. If we're below target, but in the realm of predictable routine variation, we want to make sure we react the right way. And then another mistake people make, because either their software recommends it or their previous instruction and statistical methods has asked them to use a calculated standard deviation. And again, if you're interested in this detail, I can send you some references. A calculated standard deviation makes a number of assumptions about the underlying statistical distributions that just turn out to not be good assumptions in this world. So those are some of the things I would caution you about. Using process behavior charts can help us avoid these first two mistakes. But then in the course of using process behavior charts, I would encourage people not to make those two mistakes. So we're getting close to being finished here.
Mark, I'm surprised that wasn't another David Pumpkins reference. You sure went all in on David X chart pumpkins today.
Yeah, I mean, I love David X chart pumpkins, but I think more importantly, I'm crazy for process behavior charts. Oh, and the internet's buffering. Any questions? End of our bad SNL sketch, or I should take the blame for that. My bad SNL sketch.
Well, while we're waiting for questions to come through, we have some announcements. Check out KaiNexus webinars at kainexus.com/webinars, including the Just or A3 webinar that we mentioned earlier. And check out the blog at blog.kainexus.com. You can find lots of information about control charts on the blog and lots of information about improvement in general. Now, if you'd like more information about using KaiNexus for control charts, if you're a customer, contact your customer experience representative. If you're not a customer and want to be one, send me an email, reach out to me on Twitter, or hit one of the contact sales buttons on the KaiNexus website. Now, if you'd like to watch Mark's previous non-Halloween themed webinar on this topic, you can find that along with a tutorial on creating process behavior charts in our webinar library or our YouTube channel. Our next webinar is going to be on November 28th, presented by Mike McGowan, the Director of Process Excellence at Marietta Memorial Hospital. I think he is in the audience today. The title is How One Community Hospital is Creating a Culture of Continuous Improvement. And you can register, or we'll be able to register shortly at kainexus.com/webinars. We hope you join us there. And then I'm going to plug my own webinar series. For our customers, tune into the next Training Team Office Hours webinar, otherwise known as the Banner Rippy Show, at the end of November. It'll be our last and greatest webinar of the year. You can find all of our past webinars by going to kainexus.com/webinars and then hitting the button with Ryan and I's face on it. Now it's time for Q&A here.
And thanks, Matt. The first, I don't know how many people asked, like, are we supposed to know who David X Chart Pumpkins is? Like, is he some guy from local commercials, or what is he? I don't know. Maybe there were some more substantive questions.
So the first one that I see right here is, are we going to have the recording of the webinar after the session? Yes, the recording will be sent out.
Yeah, maybe against my own better judgment, but yeah, I think we're going to make this recording available.
Okay, Mark, what are your suggestions on how to best pitch to leadership the needed change in using run charts with only a target or goal line to process using process behavior charts? This is from Jenna.
All right. Thanks, Jenna. Probably the best way to approach this has nothing to do with a red wig or a fake cigarette, but yeah, this is tough because, you know, I talk about this in chapter 9 of the book. You know, the curse of an engineer, or sometimes the curse of an entrepreneur, is that you've got an idea that's better, and you could prove in some mathematical or scientific way that the approach is better. But if people don't see a problem in the way they're currently doing things, they're not going to be interested in solutions. So this creates a great change management challenge. I've seen, you know, I've talked to people who've gone and said, well, you know, I'm just going to try making some charts, and I'm going to try the methodology somewhere. I'm going to try to show leaders, you know, here's what you're looking at on your board. Maybe even just show them a run chart if you're not using those with your metrics. Run charts can be a great baby step, which can be a good change management strategy, instead of, you know, maybe overwhelming people with control charts and math and what are those limits. And, you know, start with run charts and maybe just draw the average line and ask leaders, well, you know, do you see more from this? And, you know, you could maybe try to bring them along that way. There are some environments where, you know, if you have the opportunity as a process improvement coach, leaders will ask for input. What do you see that we could be doing better? How would you suggest we track metrics? And maybe you can seize an opportunity like that to do a pilot. You could try doing a class internally. I would suggest if you're going to show somebody a webinar about this, maybe go back to one of these other webinars that might be less off-putting to somebody who doesn't, who isn't in on the Halloween joke today. But you can expose people to the idea, you can create awareness, but then you've got to figure out what are their motivations to change. If they're really dead set that they like the way they manage, that reacting to reds and below average data points feels good, you might not make a lot of progress. But that's the real challenge here. Having the right answer, if you will, doesn't necessarily lead to adoption, but you can try. You can find somebody who's willing to be an early adopter, perhaps.
Great answer, Mark. So we have a comment. Love the humor, lightheartedness, Tom Hanks, and of course the information today from Jason. Thank you very much. Here's a good one, Mark. How far do you see the future of run charts and control charts in the WRT Industry 4.0? Now, Industry 4.0 refers to the fourth industrial revolution and the introduction of computer and cyber systems into that manufacturing environment. So how do you see that process working with the future of run charts?
Yeah, that's a good question. I don't see control charts, process behavior charts becoming obsolete. I mean, the core methodologies are 100 years old, which doesn't make them bad. Process behavior charts were first developed, I believe, in the early 1940s. So, in a lot of ways, it's like, I think these are, proven, solid, valid techniques. Now, some of the technology around them has changed. When I started at General Motors in 1995, we had people on the shop floor, a lot of whom didn't even have their high school degrees, plotting the data points and evaluating control charts with pencil and paper and by hand. Now, they might not have calculated the limits. It might have been an engineer, quality person who did that, quality control department person. So they can be drawn by hand. I've seen, current day practice in hospitals and other settings, the charts can be drawn with a pencil or a marker up on a bulletin board for people to display. We can use Excel. We can use different software systems. So it would be hard to, maybe I don't know enough about Industry 4.0 to think about what would change about processes, predictable processes, process improvement, mindsets. I don't really see how that would change. I did have someone pose a question about, well, shouldn't we use artificial intelligence to determine what the signals are? I'm like, well, in a way, these charts, these simple charts, I'm going to pull up an example here. You might call this a form of artificial intelligence. It is eliminating a lot of the gray area or the judgment calls around whether we have just noise or whether we have a signal. There's probabilistic chance that this data point is not a signal, but process behavior charts filter out roughly 99% of the noise. So the way the rules are set up, the way the limits are calculated, we're very unlikely to have false signals in the data. So I guess I would call that a form of AI, if that's helpful.
Well, so this leads to my next question. This was from Greg. What led you to change the terminology from control chart to process behavior chart? Was it a better explanation of both the positive and negative indicators in the charts?
Yeah, well, so again, Don Wheeler deserves credit for the phrase process behavior chart. So if we go back to his book, which I really recommend, the first edition of his book, Understanding Variation, let me try to find it in the slides here. The first edition used the terminology control charts. And I think there's a lot of, a lot of baggage with that word control. This isn't about controlling people. Are we trying to control the process? Are we trying to decide when it's out of control? I mean, out of control, this is kind of, the basis of the costume. Out of control sounds has implications like, well, that person's out of control. He came up with the term process behavior charts because I think it's pretty straightforward. It's a chart that explains the behavior of the process. It's a little bit less loaded of a term. in Six Sigma methodologies, people talk about the DMAIC cycle, which in define, measure, analyze, improve, control. I've heard some people say, oh, well, you don't use a control chart until you're in the control phase of Six Sigma. And I'm like, no, I don't think, I think that's confusion more than fact. So, I mean, those are the reasons that I've heard Dr. Wheeler give. I think it's a good term that works across different industries. A little bit less loaded of a term. But hey, I'm going to jump in with a comment. Mike McGowan, who is presenting our next webinar, he texted me. He said, "Well done," and he says he loved the Spider-Man. So here we go. I'm going to put poorly copied and pasted mask. Mike, if you're still listening, you don't need to wear a costume next week. We do have a friendly wager on the Northwestern Notre Dame game, but I don't think that friendly wager. I'm a Northwestern guy. He's a Notre Dame guy. I don't think that friendly wager involves somebody wearing the other school's gear on the next webinar. Mike, let's talk about that offline. Sorry.
So a question from Trevor came in. What assumptions need to hold true about the data or the process in order to act on the output of the PBC charts in the way you've described?
What can you say that again? What assumptions need to be true about the process?
What assumptions need to hold true about the data or the process in order to act on the output of the process behavior charts in the way you described?
Yeah, so hopefully I'm answering the right question, but the precursors, the forms of control chart that were invented before the XMR chart, aka the process behavior chart, include U charts, P charts, C charts, if I have this right. There's charts that use calculated standard deviations. When I took Don Wheeler's workshop earlier this year, he emphasized that a calculated standard deviation requires certain assumptions of a really homogeneous process and underlying distribution of the data. There are, I think, in some of these methodologies, assumptions about the normality of the underlying data. And the great thing about the XMR charts or the process behavior charts is that it's really robust. We don't need normally distributed data. You can have uniform data, different distributions, and the XMR chart, in using the moving range average to calculate the limits, is more robust in a situation where the system is changing. So methodologies that would call for a calculated standard deviation are going to cause problems if we have a system that's not really stable and predictable. That's my understanding of it. And if you want to follow up with me via email or Twitter, I can point you to this. I'm trying to give my best explanation. My view of it is more of a practitioner view. I trust Don Wheeler and his PhD. I don't mean to try to punt on responsibility for answering that question, but would be happy to provide some of the sources on that.
So Mark, we still have 3 or 4 questions left. I think we have time for one more. We'll make sure that we follow up, or you can reach out via email or Twitter or whatever the best way is to get those answered. The last one it's from Dante, and he says, I'm a Six Sigma certified and new to creating and reading control charts. Can you recommend some reading or online material for a beginner like me?
Well, so Don Wheeler's book, Understanding Variation, is designed for beginners. My book, Measures of Success, is also designed for beginners. I'm not trying to replace Don Wheeler's book by any means, but I think my book has some other wrinkles and connections to lean management that aren't there in Wheeler's book, as great as his books are. I would also recommend. We've got previous other webinars that I've done. The bonus content webinar about how to create a control chart. We'll step through in a little bit more step-by-step detail about creating the charts, and some of the other webinars I've done use other examples and other scenarios that talk about these signals and learning when it's most appropriate and helpful to respond.
Awesome.
Responding to a change in the data because it's a signal. That's how I should have said that.
Well, thanks so much, Mark, for all the lessons. Like I said, I highly recommend checking out Mark's book, whatever level you are in process control charts. And thank you for everybody for joining us today. This has been Matt Banda with KaiNexus, and we'll see you next time.
Thanks, Matt. Thanks, everyone.